Have you ever really thought about why some things snap, some things just bend, and other things seem to last pretty much forever? Well, it turns out that every material all around us, from the phone in your hand to the bridge you just drove over, it has a kind of secret language. And today, we're going to learn how to speak it. Let's dive in. It all starts with a super simple question, one you've probably even tested out yourself. Why does a rubber band snap right back to its original shape, but a paperclip, well, once you bend it, it just stays bent? The answer isn't magic, not at all. It's science, specifically the science of mechanical properties. And this brings us to a really important point we need to get straight. We're not talking about physical properties here, like what color something is or how much it weighs. No, we're focusing on mechanical properties, which is really just a fancy way of asking, how does this stuff behave when you push it, pull it, or twist it? It's all about performance under pressure. So to really get a handle on this, we're going to break it down into 4 parts. First, we'll look at what it actually takes to break something. Then we'll get into how things bend and change their shape. After that, we'll see how materials survive all the wear and tear of daily life. And finally, we'll see how designers and engineers put all this knowledge to work. All right, first step, resisting the break. This is all about the ultimate limits. We're talking about how much a material can possibly take before it just fails completely. Let's kick things off with tensile strength. I want you to picture a game of tug of war. Tensile strength is basically just a measurement of how hard you can pull on that rope right before it snaps in two. It's the ultimate test of a material's ability to just hold itself together when it's being pulled apart. Okay, next up is shear strength. This time, think about a deck of playing cards. If you push the top card sideways, the whole deck kind of slides and comes apart, right? That's shear. So shear strength is a material's ability to resist that internal sliding. And this is absolutely critical for things like bolts and screws, which are always dealing with that kind of slicing force. Now, strength isn't just about one big, single event. It's also about endurance. And that brings us to fatigue strength. Remember our paperclip from the beginning? If you bend it back and forth in the exact same spot, it gets weaker, and then eventually, it breaks. That's fatigue. This property tells us exactly how many of those repeated cycles a material can handle before it gives up. So we've talked about things breaking, but what about what happens before that? What about just bending? This is the story of how materials deform, and more importantly, whether that change is just temporary or if it's permanent. And here we are, right back to our original question. On the left, you've got elasticity. That is our rubber band. You stretch it, you let go, and it snaps right back. That change is totally reversible. But on the right, you have plasticity. That's our paperclip. You bend it, you let go, and it just stays in that new shape. The change is permanent. They're two totally opposite reactions to the same force. Okay, so if a material can be both elastic and plastic, where's the dividing line? What's the tipping point? Well, that line is called the yield strength. It's the literal point of no return. Push a material just a little bit, it's elastic. But push it past its yield strength, and now it's plastic. It has changed its shape for good. Let's walk through that little journey from elastic to plastic. First, you apply a little bit of force, and the material bends elastically. Easy enough. Then you remove that force, and poof, it pops right back to how it was. But if you push it past that yield point, you get plastic deformation. And now, when you let go, the material holds on to that new permanent shape. You've officially reshaped it. Now, plasticity actually comes in a couple of different flavors. One of them is ductility, and ductility is all about stretching. It's a material's ability to be pulled and drawn out into a long, thin shape without snapping. I mean, the whole reason we can have those incredibly fine copper wires inside all our electronics is because copper has amazing ductility. And then you've got malleability, which is kind of like ductility's cousin. So instead of being pulled, a malleable material can be hammered or pressed or rolled into a super thin sheet without shattering. Gold and aluminum are famous for this. I mean, think about gold leaf or even just a simple sheet of aluminum foil. That's malleability in action, right there. Okay, so we've covered pulling and bending. Now for section 3, surviving wear and impact. This is all about how materials hold up against the scrapes, scratches, and sudden blows they have to face in the real world. The first line of defense here is hardness. This is a material's ability to fight back against being scratched or dented or worn away. A diamond is incredibly hard, right? That's why it can cut glass. Your phone screen is specifically designed for hardness so it doesn't get all scratched up by the keys in your pocket. And we don't just guess how hard something is. It's all very precisely measured using these standardized tests. You can see a few of them here, like the Brinell, Rockwell, and Vickers tests. They all work on a pretty similar idea. You take a super hard object, you press it into the material's surface, and then you just measure the size of the dent you left behind. The smaller the dent, the harder the material. Simple as that. Now listen up, because this is a big one. Do not confuse hardness with toughness. They are totally different things. Toughness is not about resisting a scratch. It's about absorbing a sudden, powerful hit without shattering into a million pieces. A ceramic plate might be very hard, but it's not very tough. You drop it, it's gone. A car bumper, on the other hand, is designed to be really tough. And toughness becomes even more critical when you're in extreme environments. Why? Well, because cold temperatures can make a lot of materials dangerously brittle. So for something like an offshore oil platform way out in the Arctic, the steel has to be incredibly tough to handle those icy waves and impacts without just cracking apart. In situations like that, toughness can literally be a matter of life and death. Okay, so we've got strength, plasticity, hardness, and toughness. What is the point of knowing all this stuff? Well, in our final section, we're going to see how it all comes together. For an engineer or a designer, these aren't just vocabulary words. They are a palette of options for building our entire world. And there's one more crucial property in that palette: brittleness. This is basically the exact opposite of ductility and toughness. A brittle material like glass or ceramic, it fails suddenly. It doesn't stretch, it doesn't bend, it just shatters. No warning. Sometimes that's actually useful, but a lot of the time it's something engineers have to be very careful to design around. And this really brings us to the most important takeaway of all. Every single object in our world is the result of a choice. An engineer had to look at the job that object needed to do and carefully balance all of these properties. A kitchen knife needs to be hard so it can hold a sharp edge, but not so brittle that it shatters. A bridge cable needs immense tensile strength and fatigue resistance. It is always a complex, fascinating balancing act. By understanding this language of materials, we can literally build the world around us. So now that you have the vocabulary, strength, toughness, plasticity, hardness, take a look around you and think about the future. What are we going to build, and what materials will we choose to do it?